All of you, good morning, my dear student. Today class discuss about the subject name is heat power engineering, 5th unit, 5th chapter. See subject code C18M-402C, HPE DME second year. In this steam turbines, in this chapter, in previous class we learn about classification of steam turbines, working principles of working of steam turbines, impulse turbine, reaction turbines, comparison of impulse and reaction turbines, In last class we learn about this topic. This topic is completed in last class. Classification of steam turbine, working principles of steam turbines, working principles of impulse turbines, reaction turbines, comparison of impulse and reaction turbines. This topic is completed in last class. On completion of this period, you would be able to know. Today we discuss about this topic. Today class, this topic may be completed. Today class we discussing this topic to identify various blade angles. To draw velocity triangles. Work done axial thrust, power and efficiencies. Work done axial thrust, power and efficiencies. This topic in today class we discuss about this topic to identify various blade angles, to draw velocity triangles, work done axial thrust, power and efficiencies. This topic is completed in today class. Velocity triangles. The blade friction is 0. Assumption made, the blade friction is 0. U blade velocity, units is meter per second. Small u is a blade velocity, meter per second. Capital V1 is steam inlet velocity. V1 is a steam inlet velocity, units meter per second. VR1 steam inlet relative velocity, R1 means relative. Steam inlet relative velocity, units meter per second. VF1 steam inlet flow velocity, meter per second. Steam inlet flow velocity, meter per second. VW1 steam inlet Verrill velocity, meter per second. Steam inlet Verrill velocity, meter per second. Alpha steam inlet angle or nozzle angle. Alpha is a steam inlet angle or nozzle angle. Alpha is a steam inlet angle or nozzle angle. Theta is a phi is a inlet blade angle. Assumption made, the blade friction is 0. U is a blade velocity, meter per second, units. V1 is equal to steam inlet velocity, meter per second. VR1 steam inlet relative velocity. VR1 is a steam inlet relative velocity, meter per second. VF1 steam inlet flow velocity, meter per second. Steam inlet flow velocity, meter per second. VW1 steam inlet Verrill velocity, meter per second. Steam inlet Verrill velocity, meter per second. Alpha is a steam inlet angle or nozzle angle. Alpha is a steam inlet angle or nozzle angle. Phi inlet blade angle. Similarly, capital U is equal to blade velocity meter per second. U1 is equal to U2 is equal to U. V2 steam outlet velocity. V1 is a steam inlet velocity, V2 is a steam outlet velocity. VR2 steam outlet relative velocity. VR1 is steam inlet relative velocity. VR2 is a steam outlet relative velocity. It is meter per second. VF2 steam outlet flow velocity. Steam outlet flow velocity. F2 means outlet. F2 means outlet flow. Steam outlet flow velocity meter per second. VW2 steam outlet viral velocity meter per second. Steam outlet viral velocity meter per second. Beta steam outlet or nozzle angle. Steam outlet or nozzle angle. Phi outlet blade angle. Phi is a outlet blade angle. Similarly, U is equal to blade velocity meter per second, U1 is equal to U2 to U. V2 is equal to, V2 is a steam outlet velocity meter per second, VR2 steam outlet relative velocity meter per second, VF2 steam outlet flow velocity meter per second, VW2 steam outlet viral velocity meter per second. Beta is a steam outlet or nozzle angle. Phi is a outlet blade angle. Effective component of steam which produces tangential force and causes wheel to rotate is while component. The velocity of flow is responsible for producing axial thrust on wheel. The velocity of flow is responsible for producing axial thrust on wheel, as shown in this figure. Effective component of steam which produces tangential force and causes wheel to rotate is while component. The velocity of flow is responsible for producing axial thrust on wheel. The velocity of flow is responsible for producing axial thrust on wheel. Draw U as horizontally as shown in figure. U number 1 figure, draw U as horizontally as shown in figure. This is a nozzle, blade, alpha, U, capital U, as shown in this figure. These are draw UA horizontally as shown in nozzle, alpha, U. This is a blade. Draw V1. Draw V1 in direction of flow at angle alpha. Draw V1 in direction of flow at angle alpha. This is a nozzle. V1, this is a direction, velocity. Steam inlet velocity V1. Angle is alpha. Steam blade. This is a blade B. B means blade. U. Total energy. So u means blade velocity. Alpha is a angle, b is a blade, u is a blade velocity. Nozzle. V1 in direction of flow at angle alpha. Nozzle. Steam inlet velocity. V1 is a steam inlet velocity, is flowing alpha angle. Blade velocity, u is a blade velocity, as shown in this figure 2. Three, join u and V1 to get VR1. Join u and V1 to get VR1. Both are joining, u and v are joining. We get the equation VR1 alpha angle. Steam inlet velocity is V1, angle is alpha. Blade velocity, u is a blade velocity, blade. VR1. Blade inlet velocity, inlet relative velocity. VR1 is a inlet relative velocity, as shown in figure 3. This join u and V1 to get VR1. V1 is a steam inlet velocity, VR1 is a steam inlet relative velocity. This angle is alpha, u is a blade velocity. This is a process of the as shown in this figure. Triangle is forming is triangle. Tangential. Hypotenuse is V1, opposite by hypotenuse. Adjacent is VR1. In this triangle, as shown this figure, alpha is hypotenuse is steam initial velocity, adjacent is steam initial relative velocity. This middle is angle is alpha. Then internal energy u, blade velocity, as shown in this figure. Extend u. Fourth is extend u. Extend u. V1 is a steam inlet velocity, VR1 is a steam inlet relative velocity, angle is phi, as shown in this phi. These are blade velocity. As shown in this figure. Extended u. U may be extended. Extends blade velocity. U is equal to, as shown in this figure, alpha V1 VR1 phi. Phi angle as shown in this figure. Draw a vertical line. Draw a vertical line. Therefore, in this triangle, V1 steam inlet velocity, VR1 is a steam inlet relative velocity, angle is alpha phi. Draw a vertical line. Draw the vertical line. VW1. U is a blade velocity, as shown in this figure. This is a draw a vertical line. this figure, draw a vertical line VW1, this vertical line. Draw a vertical line. Steam inlet wipe velocity. V is a blade velocity, given as a steam inlet velocity. We are on steam inlet relative velocity, steam inlet flow velocity, steam inlet while velocity, steam inlet angle or nozzle angle alpha. Phi is inlet blade angle. Blade velocity, steam outlet velocity equal to steam outlet velocity. We have the steam outlet relative velocity, steam outlet flow velocity, VW to steam outlet while velocity, steam outlet nozzle or steam outlet nozzle angle, steam blade outlet blade angle. Effective component of steam which produces steam. Tangential force and process while to rotate is while component. The velocity of flow is responsible for producing axial thrust on wheel. Extended U. Steam inlet while velocity VW1 has a draw a vertical line this way. Draw a vertical line. In this figure, V1 is a steam inlet velocity, VR1 is a steam inlet relative velocity, VW1 is a steam inlet while velocity, U is a blade velocity, phi theta phi, blade angles, phi is a nozzle angles, similar draw for a outlet triangle. Similarly, draw for a outlet triangle. Similarly, draw for outlet triangle. Draw VR2 in the direction of steam outlet at angle phi to horizontal line. Angle phi is to the horizontal line. In this figure, V1 is a steam inlet velocity, VR1 is a steam inlet relative velocity, VF1 a steam inlet flow velocity, VW1 a steam inlet while velocity, U is a blade velocity, VR2 is a steam outlet relative velocity. VR2 is a steam outlet relative velocity as shown in this figure. This is a similar draw for outlet triangle. Draw VR2 in the direction of steam outlet at angle phi to horizontal line as shown in this figure. In this figure, steam inlet velocity is steam inlet relative velocity, steam inlet flow velocity, steam inlet while velocities, blade velocities, nozzle angles, steam outlet velocities is as shown in this figure. This relative velocity there in this figure showing in similar to the outlet triangle. This is it. Seventh one is draw you like inlet triangle. Draw you like inlet triangle. This is the inlet triangle. In this therefore is outlet triangle. This is the inlet triangle. Seventh one, draw you like u means blade velocity like inlet triangle. Draw u means blade velocity like inlet triangle. Blade velocity is draw blade velocity like inlet triangle. This way to draw this figure. V1 is a steam inlet velocity. VR1 is a steam inlet relative velocity. VF1 is a steam inlet flow velocity. This is a phi is a marginal angles. U is a blade velocity. V1, VW1 is a steam inlet while velocity. This is a VR2 is a steam outlet relative velocity are shown in this figure. This is a draw u like inlet triangle. This is a draw u like inlet triangle. Next we are discussing draw u like inlet triangle. Next, join u and VR2 to get V2. These two are joining, we will get the outlet velocity of steam outlet velocity. We will get the steam outlet velocity V2. Both are joining blade velocity and steam outlet relative velocity. Both are joining to get the V2. Join u and VR2. Join u means blade velocity and VR2 means steam outlet relative velocity. Both are joining. You get the equation V2 value. You get the V2. V2 means steam outlet velocity. In this figure, draw this figure. Both are joining to get the V2. In this figure, V1 is a steam inlet velocity. VR1 is a steam inlet relative velocity. VF1 is a steam inlet flow velocity. VW1 is a steam inlet while velocity. U is a blade velocity. This is angle phi. V2 is a steam outlet velocity. This beta angle is a nozzle angles are shown in this figure. Beta blade velocity. Draw u like inlet triangle. Join u and VR2 get V2. Extend u as inlet triangle. The blade velocity may be extended as inlet triangle. Blade velocity is extended. Extend u as inlet triangle. In inlet triangle, u may be extended. To get this figure, this as shown in this figure. U may be extended in inlet triangle. This figure is as shown in this figure. In this figure, V1 is a steam inlet velocity. VR1 is a steam inlet relative velocity. VF1 is a steam inlet flow velocity. VW1 is a steam inlet while velocity. U is a blade velocity alpha angle. U is a blade velocity beta angle. V2 is a steam outlet velocity. VR2 is a steam U is a blade velocity. This complete triangle, draw the vertical to complete triangle. In this figure, V1 also same steam inlet velocity. VR1 is a steam inlet relative velocity. VF1 is a steam inlet flow velocity. Angle is phi. V1 and AR, the angle is alpha. U is a distance, is presence of the angle. U is a blade velocity. VW1 is a inlet steam while velocity. VW2 is a outlet steam while velocity. Steam is outlet. VW2 is a steam outlet while velocity. VW1 is a steam inlet while velocity. U is a blade velocity. Beta, this is a angles. V2 is a steam outlet velocity phi. VF2 is a steam flow outlet velocity. VF2 steam flow outlet velocity. VF2 is a steam outflow velocity. VR1 is a steam outlet relative velocity. VR2 is a steam outlet relative velocity. This is a draw vertical to complete triangle. This is a draw vertical to complete triangle as shown in this figure. This figure is shown as complete triangle. Draw vertical to complete triangle. Next, 11. Make mirror image of inlet triangle along y-axis. Make mirror image of inlet triangle along y-axis as shown in this along mirror axis. Make mirror image of inlet. Make mirror image of inlet triangle along y-axis. Mirroring axis. Y is a mirroring axis. Phi alpha u. Beta phi. Alpha phi u. Alpha phi u. Mirroring axis. Alpha phi u. Phi alpha u. Beta phi. These are make mirror image of inlet triangle along y-axis. Make mirror image of inlet triangle along y-axis. Make mirror image of inlet triangle along y-axis. Mirroring axis. Alpha phi with blade angle. Blade velocity. U is a blade velocity alpha phi u. So these are mirroring axis. Again make mirror image of previous one along x-axis. Again make mirror image of previous one along x-axis. Again make mirror image of previous one along x-axis. Again make mirror. Again make mirror image of previous one along x-axis. Beta phi u blade velocity combined velocity triangle. This is a combined velocity triangle. So many velocities are combined. These triangles may be forming. This is called combined velocity triangle. So number of velocities are combined. They are forming the triangles. So many velocities are combined. The triangles may be forming. Number of combined velocities. So many velocities are combined. This triangle is forming. VW2 is a steam outlet while velocity. Steam outlet while velocity. VW1 is a steam inlet while velocity. VW1 is a steam inlet while velocity. VW2 is a steam outlet while velocity. This is a bit alpha, beta, phi angles is there. Alpha, beta, phi, theta angles may be as shown in this figure. So many triangles may be forming. VF2 is a steam outlet flow velocity. Steam outlet flow velocity VF2. V2 is a steam outlet velocity. VR2 is a steam outlet relative velocity. V1 is a steam inlet velocity. VR1 is a steam inlet relative velocity. VF1 is a steam inlet flow velocity. These are all are combined velocity triangles may be forming. 1, 2, 3, 4, 5. 5 types of triangles may be forming. 1, 2, 3, 4, 5. 5 triangles. Number of velocities are combined. 5 triangles may be forming. Triangle. In these triangles, V1 is a velocity of steam inlet while velocity. VW2 is a steam outlet while velocity. V is a blade velocity. 5 these are angles, nozzle angles, alpha, phi, beta, theta. VR1 is a steam inlet velocity. VF1 is a steam inlet velocity. Inlet flow velocity. VF2 is a steam outlet flow velocity. V2 is a steam outlet velocity. VR2 is a steam outlet relative velocity. V1 is a steam inlet velocity. These are combined velocity triangle diagram as shown in this figure. Formula. Work done per second or power mu into VW1 plus or minus VW2. Power mu to VW1 plus or minus VW2. Work done per second or power is equal to mu VW1 plus or minus VW2. Work done per second or. Their M is mass flow rate in kg per second. In this figure, their M is mass flow rate in kg per second. If beta less than 90 degree, VW2 is positive. Beta angle is less than 90 degree. This steam outlet velocity is positive. In formula work done per second or power is equal to mu VW1 plus or minus VW2. Where M is mass flow rate in kg per second. In this equation, M is mass flow rate in kg per second. Where M is mass flow rate in kg per second. If beta less than 90 degree, beta value is less than 90 degree, steam outlet velocity is positive. Beta is equal to 90 degree, steam outlet velocity is 0. Beta value is beta angle is greater than 90 degree. Beta value is 90 degree above. The steam outlet value is negative. 90 degree below is steam outlet value is positive. 90 degree above is steam outlet is negative. Beta value is 90 degree. Beta greater than 90 degree. Steam outlet value is negative. Axial thrust mass into acceleration. Axial thrust equal to mass into acceleration. Mu to Vf1 minus Vf. Axial thrust is equal to mass into acceleration. Mass m into mass u. Net velocity Vf1 is a steam inlet flow velocity. Vf2 is a steam outlet flow velocity. This blade or diagram efficiency. Blade or diagram efficiency. Blade or diagram efficiency equal to work done on blade. Work done on blade. Work done on blade by energy supplied to blade. Work done on blade by energy supplied to blade. This ratio is called blade or diagram efficiency. Blade efficiency or diagram efficiency. These two, work done on blade by energy supplied to blade. This ratio is called blade efficiency or diagram efficiency. Mu into Vw1 plus Vw2. Mass blade energy. Vw1 is a steam inlet while velocity. Vw2 is a steam outlet while velocity by half mv square. V1 square m half m V1 square. V1 square is a steam inlet velocity. 2u Vw1 plus Vw2 by V1 square. This Nm is cancelled. In this equation Nm is cancelled. This 2u to Vw1 plus V2 by numerator is taken, 2 is numerator, denominator. Vw1 plus Vw2 by V1 square. Nozzle efficiency. Next we discuss in nozzle efficiency. Nozzle efficiency. Gain in kinetic energy, enthalpy drop in nozzle. This ratio is called nozzle efficiency. Gain in kinetic, enthalpy drop in nozzle. This ratio is called nozzle efficiency. Gain in kinetic energy. Nozzle efficiency means gain in kinetic energy by enthalpy drop in nozzle. This ratio is called nozzle efficiency. Half mv square by m delta h. Enthalpy drop equation mu Vw1 plus Vw2 by m delta h. 2u Vw1 plus or minus Vw2 by 2 delta h. 2u Vw1 plus Vw2 by V1 square into V1 square by 2 delta h. V1 square by 2 delta h. Blade efficiency into nozzle efficiency. Blade efficiency into nozzle efficiency as shown in this equation, enthalpy drop equation. Mu Vw1 plus Vw2 by m delta h equal to 2u Vw1 plus or minus Vw2 by 2 delta h. 2u Vw1 plus Vw2 by V1 square into V1 square by 2 delta h. Blade efficiency into nozzle efficiency. blade efficiency into nozzle efficiency. Effect of blade friction. When steam is gliding over the blade, due to friction, relative velocity will be decreases. When steam is gliding over the blade, due to friction, relative velocity will decrease. VR2 less than VR1. VR2 is a steam outlet relative velocity, VR1 is a steam inlet relative velocity. This less than VR2 less than VR1. VR2 is equal to KVR1. VR2 is a steam outlet relative velocity constant VR1. VR1 is a steam inlet relative velocity, where K is friction factor. Where K is friction factor. This effect of blade friction. When steam is gliding over the blade, due to friction, relative velocity will decrease. VR2 less than VR1. VR2 is equal to KVR1, where K is friction factor. Summary. In this period we have learned about how to draw velocity triangles. How to draw. Identification of various blade angles. Expressions for work done, power, axial thrust and efficiencies. Expressions for work done, power, axial thrust and efficiencies. In this summary, today class we have discussed about this topic. In this period we have learned about how to draw velocity triangles, identification of various blade angles, expression for work done, power, axial thrust and efficiencies. This topic we have learn about today class. Stage efficiency steam turbine is blade efficiency, nozzle efficiency by blade efficiency. Nozzle efficiency into blade efficiency. None. This nozzle efficiency into blade efficiency. This is a stage efficiency of steam turbine. Stage efficiency of steam turbine is nozzle efficiency into blade efficiency. Nozzle efficiency into blade efficiency. If V1 is the velocity of steam supplied by a nozzle and delta is the enthalpy drop in nozzle, then efficiency of the nozzle is which one is answer? V1 square by 2 delta H. If V1 is the velocity of steam supplied by a nozzle and delta H is the enthalpy drop in nozzle, then efficiency of the nozzle is V1 square by 2 delta H. Then efficiency of the nozzle is square by 2 delta H. Assignment. Effect of blade friction. This is a effect of blade friction. Effect of blade friction. When steam is gliding over the blade due to friction, the velocity will decrease. VR2 less than VR1, VR2 K VR1, where K is friction factor. Effect of blade friction. When steam is gliding over the blade due to friction, relative velocity will be decreased. Effect of blade friction. When steam is gliding over the blade due to friction, relative velocity will decrease. VR2 less than VR. This period, this topic we have learned about. We have learned about how to draw velocity triangles, identification of various blade angles, expression for work done, power, axial thrust and efficiencies. Which stage efficiency of steam turbine is nozzle efficiency into blade efficiency. V1 is the velocity of steam supplied by a nozzle, and delta S is the enthalpy drop in nozzle. Then efficiency of the nozzle is V1 square by 2 delta H. V1 square by delta H. Delta H by V1 square. This is V1 square by 2 delta H answer. This class assignment. Explain the procedure to draw inlet and outlet velocity triangles. Explain the procedure to draw inlet and outlet velocity triangles. Combined velocity diagram for impulse turbine. Combined velocity diagram for impulse turbine. All of you, thanks. Today class is completed. Today class is over.